Hey there everyone, welcome you all to my YouTube channel. So guys, in today's video we are going to decode the architecture of Jamba, a first hybrid transformer and Mamba based language model. You can see this particular model contains transformers, Mamba and even MOE expert. So I'll be showing you all what this particular Jamba model is all about, and we'll be decoding their architecture, and even there is a summarized article from my end for you all based on this architecture. It will be a very interesting video, so just stay tuned till the end of this particular video to understand about Jamba. And if you have not subscribed the channel, do subscribe the channel and on the bell notification. Now let's dive into my computer screen and discuss more about this particular topic. So techies, you can see the research paper here. This is the Jamba's research paper, and you can see here a hybrid transformer Mamba language model, and these all are the people who have contributed to create this particular model. Okay, and it is from AI21 Labs. You can see the abstract here. We present Jamba, a new based large language model based on a novel hybrid transformer, Mamba and mixture of expert architecture. So it is combination of transformers, Mamba and MOE. Okay. So by the combination of all these three, they have created a model called as Jamba, which outperforms many of the recent LLM models. Okay. It even outperforms Llama 2 also. So I'll just show you all. It enjoys the both model familiarities, and MOE is added in some of these layers to increase model capacity. So the MOE is mainly used in this model to increase the capacity of the model. And when it comes to transformers, right, so it cannot handle the large context. So transformers is good in performing, but when it comes to the large context, transformer has some latency and it cannot handle it properly. Mamba can handle the latency, but the Mamba architecture, if you see, it has the problem of forgetting. Okay, whatever it is, like previously whatever was there, you used to not at all remember that. Okay, so when it continuously goes on training, like you can say similarly kind of RNN architecture. So to overcome this, okay, so the Mamba and transformer, they have combined both, and even they have even used MOE. Okay, what will happen here? So with the help of transformer, we can store the data and we can process the data. Whatever transformer capabilities are there, that we can take in. And with the help of Mamba, so we can like reduce the latency and the training speed will be increased. Okay. So there is a article from, you can say blog from Jamba, I mean A21 Labs related to Jamba. So you can see here what they are saying. We are thrilled to announce Jamba, the world's first production grade Mamba based model, by enhancing Mamba structure state space model SSM technology and elements of traditional transformer architecture. Okay, you can see here what Jamba can do. Hello Swag. So in Hello Swag, it has 87.1%. ARC challenge, it has 64. We know, great. So you can see the percentages. MMLU, in that it has 67%. So there is some key features also, and even you can see the image here, what it is trying to break down. Common benchmarks of Jamba compared to Mixtral, Gemma 7B, Llama 2 and Llama 2 13B. Okay. Now the key features are: first, production grade Mamba based model built on a novel SSM transformer hybrid architecture. In a sense, see, Mamba was there from first only, before transformers also Mamba was there. So what was the problem is, based on Mamba, until now no one have researched anything, and there is no official like you can say production grade model which we can use. All the models you see, Llama 2, Gemma, everything is based on transformers architecture only. But based on Mamba, there were no architecture or no production grade LLM model. So this is the first Mamba based LLM model. Okay, production grade one. And it is 3x output on long context compared to Mixtral 8 into 7B. So they are claiming that it is 3x speed in the form of long context compared to Mixtral 7B. So it can outperform Mixtral 7B in this, and democratizes the access to a massive 256K context window. Okay, so this one they are claiming, so it can get the access of it. And the only model in this size class that can fit up to 140K context on a single GPU. So until now there were no models which can fit 140K context tokens into a single GPU. Okay, So they are claiming that Jamba can do that. Released with open weight under Apache 2.0. So you can open this particular, if you just search for Jamba's GitHub, you will get it. You can open that and you can fine tune it because it's completely open source model. You can use it for your purpose also. It is just with the Apache 2.0 license and available on Hugging Face and coming soon for NVIDIA API catalog. So now it's already available on Hugging Face. If you just click on this and click on new tab, so you can see here it is already available on Hugging Face. Okay, so you can see the codes here. You can just click on this. You can use it. This with the help of this code, you can load it. You can see the run model code and how you can load the 8-bit model, how to load the model in 8 bits. So there is some example out of it, how you can fine tune it, okay, with the help of PEFT. So you can just casually try out these codes and whatever LS swag and everything, the benchmarks you saw there, the same benchmarks are here, okay. And when it comes to their architecture, right? So this is the Jamba's architecture. You can see this is the architecture and what it consists of. So Jamba consists of a transformer layer and a attention MOE layer, okay, and a Mamba layer also, and even a Mamba MOE layer. So now if you see here, this is the normal architecture, okay. First there is a Mamba layer, and after this Mamba MOE layer is added. Then again there is a Mamba layer, MOE layer. Only the transformer will come in between here after this layers. So only one place the transformer comes, and this again here MOE layer and Mamba and this one. So there is no attention MOE layer used here, but they have given it. I guess in transformer layer they have internally used attention MOE layer. So you can see here in transformer layer what we get normally, you know, right? The transformer layer has RMS normalization, attention, and POS, positional of encoding, and RMS normalization and multi-layer perceptron, MLP. Okay. And same for Mamba also. When it comes to Mamba layer, RMS, Mamba architecture is there. Okay, there is something Mamba, and even the POS, RMS prop, and MLP. So that's all. And their MOE they have added. So this, after adding all this, it becomes a layer. Okay, this particular layer is found out. This is the Jamba's block diagram, or you can say even their architecture layer. So if let me scroll down a bit, I have in my pen. Okay. So if I just scroll down here, there is a Mamba architecture. So you can see here what they are claiming. So in Llama 2, you have, okay, one second. Yeah, that was by mistake. Okay, now you can see here Llama 2, which has 6.7b available parameters. Active parameters also are same, and even 128 bits of 128 GB. It has the KV catch. Okay, just a second, guys. Okay, so 128 of KV catch. So when it comes to Mixtral, what they are saying, Mixtral has 7.2. Okay, Mixtral 7B. Okay, and Mixtral 46 and 12. So what Jamba is having, so you can see a 52 billion parameters. Jamba is having 52 billion parameters, 12 billion active parameters, and KV cache size of 4 GB cache memory. Okay. In terms of output, with short sequence, attention operations like take up a small fraction of the inference and total flip-flops. However, the long sequence attention hogs most of the compute. In context, Mamba layers are more compute efficient, thus increasing the ratio of Mamba layers improves the thought process, especially in long sequence. What does this term means that when we add attention operations and when we try to perform the model, okay, however it can capture the long sequences, okay, but when it comes to the computation, so it might take more time, okay. So to reduce that computation, what they are suggesting is you can add more Mamba layers according to your your choice, and you can, the more layers you add related to the Mamba, so the increase of the ratio of Mamba layers, it will improve the output, and especially in long sequence. What they are claiming is when you add them more, so you can increase the accuracy, or you can expect the better results compared to the previous results, and even the computation will be very fast. Okay. And you can see here, so if we scroll down a bit, Jamba implementation in single 80 GB CPU. Okay, so if you perform in a single 80 GB CPU, what they are stating here, so if you use Mixtral, Llama 2B, okay, Llama 2B. So if you use Llama 2B, it can go up to between 0 to 20k tokens, okay. More than that, it cannot go. But when you go with the Mixtral's 18 to 7B, it can go approximately between 60 to 80 tokens, okay, 60 to 80k tokens. More than this, even this is not possible. But when you see our Jamba. So in Jamba, you can see it can go up to 140k tokens. So Jamba can achieve approximately 140k tokens with one single 80 GB GPU. So now you can see how computationally good and fast Jamba, and even it is storage friendly, you can say, and even especially GPUs friendly. Now we are using so much of GPUs, like even the cost friendly. So the more GPUs you use, the more cost it becomes. So here you can say Jamba is a kind of cost friendly, and even you're using only one GPU of 80 GB, you can achieve 140k tokens. That's more than enough. Okay. So let me go further now. So what is thought process analysis? Okay. So here you can see this is the thought process analysis. Went to my pen today. Let me take a different color. We present a result of thought put in two specific settings. In the first setting, we have varying batch size of single A100 80 GB GPU in a quantization, so 8K content length, and it's generating shows that Jamba allows processing on large batches, increased outputs. Okay, so what they are telling here, they are showing in two different contexts. Okay, in two different specifications or settings, they are showing the thought process. So what they are saying here, you can see a batch size. Okay, when you perform the batch size of a single thought process GPU, you can see here Jamba is taking up to 16. Okay, but if you see the other batch sizes, you can see a Llama 2 is last till 4. Okay, it can make only 4 batch sizes. It forms in 4. Okay, apart from that, Mixtral at 8. Only Gemma is the one which can perform the height, like you can say, it can stay till 16. Training infrastructure and data sets, you can just go through this. You can see here Llama 2B benchmarks and everything, like whatever benchmarks are there, and comparisons and aggregations, everything is there, aggregates. So you all can just go through this architecture in more detail. Okay, so you will understand a bit better. So what is the effect of MOE? Everything is mentioned here. So if I go back to the article which we have written, you can see an introduction to Jamba. The key innovation of Jamba lies on the hybrid architecture, addressing the limitations inherited in traditional transformer and recurrent neural network models, while transformer struggles on long contexts, okay, and slow inferences. RNN face challenge in training efficiency and capturing long distance relationship. So to bridge this particular gap, right, like the long context size where it struggles, that one RNN doesn't. So they took RNN for that, and the training efficiency and capturing long distance ratio. So transformer fails. So they have taken both of them and they bridge the gap and they build a model using both of these models. Okay, so you got it. And here's the Hugging Face one I showed you all, and I have even explained this architecture. Okay, and apart from this, the summary in different degrees of freedom of Jamba architecture, the number of layers, AM ratio for attention to Mamba layers, and E is for how often to use MOE instead of single MLP. Okay, there is even something called as here, you can see a Jamba block consists of one layer mixed of ratio of AM indicating A attention layers and M for Mamba layers. A is for attention layers, that is transformers, M for Mamba layers. Additionally, some MLPs with Jamba may be suitable with MOE layers. So what they are claiming, some multi-layer perceptrons which are in Jamba may be suitable for MOE layers, aiding the augmenting model specifically while maintaining a manageable number of active parameters. The MOE model can be applied to MLPs every E layers, often on the choice of the possible experts per layer with the routine selecting of top K. Okay. So what does he? How often the MOE instead of a single multi-layer perceptron? So how often they have used MOE instead of a single MLP, and total number of expert layers per layer, total number of expert per layer. Okay, K, number of total experts used on each token. Okay, for that. Jamba implementation of single 80 GPU, I have told you. Output analysis. So you can see a output analysis is good explained here. We present result of output analysis in two specific scenarios to illustrate Jamba efficiency and compare with a large language model. Okay. In the first scenario, from the above image, a varying batch size of a single A180 GPU and int8 quantization, Jamba demonstrates a remarkable 3x increase in output process than Mixtral, okay, compared to Mixtral. Despite of having similar active parameters, Jamba efficiency to process large batches efficiently sets in part. Okay, that was the thought process one, which is of using a single GPU of 80 GB. In the second one, you can see we are using 100 A100 GPUs. Okay, without quantization and varying context length. Jamba superiority becomes evident, particularly in handling long context, even without the optimization enjoying by purely transformer models. Okay, and Jamba outputs outperform Mixtral by 3x at context length of 128K tokens, and optimizes the efforts of Jamba continue to evolve its output advantage is expected that further widen. So what they are telling is, when you're using a hundred GPUs, here also when we are having long context also, and without using any optimization techniques or without using any int8 quantization techniques, only if you're using GPU and running also, so you can see here Jamba is outperforming Mixtral with its 3x of the Mixtral. So okay, by its context length of 128K tokens. So training infrastructure and evaluation, this is already mentioned. Okay, long context evaluation, you can just go through this article for more detailed information. So why does the combination work? Attention Mamba and attention Mamba. So you can see here for attention it's 84%, Mamba it's IMDb, okay, and QUAC, okay. Pure Mamba model struggles in tasks requiring the context learning, production answers inconsistent with expected formats. Okay, here you can see the hybrid attention Mamba model successfully adhere the input output format, struggling the importance of attention mechanism in the context learning. So you can see here compared to the like these both layers, so the hybrid model is performing very well. It's demonstrating here. You can see here the effect of MOE. MOE improves the performance of the hybrid attention Mamba architecture even at large scale. Okay. Integration of MOE with the hybrid architecture enhances model capacity while maintaining manageable compute requirements. Okay, so what they are stating, so these are the two topics, 2 points we can say where it works well. Stabilizing Mamba at large scale. Training Jamba models at large scale encounter stability issues, particularly with large loss spike in Mamba layers. So the attention of RMS normalization is initial actuation, stabilizing the training and mitigating the loss spark during the efficiency. So when you directly train the Mamba model, okay, there is a chance of getting like stability issues. To overcome that, so they have used RMS normalization, okay, with the Mamba layers. Jamba does not require explicit positional information. What they are stating is with evaluation of Jamba architecture with and without explicit positional information shows the similar result. You can see here. So the first one is with the explicit positions. Okay. Second one is without the explicit positions. You can see there is a kind of similar output. You can say whatever they are benchmark they are showing in this. You can see it's a kind of similar. Only there is 10% of vary. So you can say with positional information or without positional information, Jamba can perform the things very well. So conclusion. Jamba introduces a new architecture blending attention and Mamba layer with MOE modules. Okay, it was great that they have combined both transformers and Mamba. So if you want to know more about Mamba architecture, right, just comment below. I'll make a detailed video related to Mamba architecture and I'll try to explain about that. So Mamba was there even when the transformers was introduced. So what transformers will do? It will use encoder decoder architecture. But this Mamba, this will use RNN by LSTM. By using this, they want to create a kind of model or else a kind of LLM model which can perform the things very well compared to transformers. We can say like Mamba is a competition to transformers. So the model offers flexibility in balancing performance and memory requirements. Okay. High output analysis is suitably for various language processing tasks. So you can see here with 120 12-bit active and 52-bit total available parameters, Jamba supports context length of up to 256K tokens. Okay, this is the highest. So you can just go through this also. Need of high stack pressuring testing LLMs and all these architectures. I mean, this GitHub repos are related to Jamba. This one Jamba only. The process is mentioned here. How you can run this LLM model. You can just go through this. Okay. I hope I explained you all better. Okay. So you all can just go through this article and also you can just go through this particular research paper also. I'll be updating both the links below this particular video. You can definitely check out them and you can try to understand it. I have just given a basic overview, higher level overview. You can just read this research paper clearly. You will definitely understand things very well. Okay. So till here, everything is like until page number 12, you have everything. So just read till here. Okay. You can see here. So you can just read this. This is very interesting. Okay. About this particular model. So meet you all in the next video. Bye bye.